weapons demand modern target or efficient crew training. Whether the weapon be a guided missile, a deadly, heavily armed, rocket-firing jet interceptor, early warning radar net, or radar-controlled anti-aircraft artillery, all must be geared to flight speeds of enemy aircraft. Obsolete aircraft converted to drone use do not provide adequate performance for effective target work. Jet fighters have rendered the sleeve target obsolete, and except for specialized training, the same thing has happened to small piston-engine drones. By contrast, a high-speed jet drone missile is now available as a truly modern target. Ryan Aeronautical Company's pilotless Firebee simulates jet fighter performance in the 250 to 500 knot speed range at altitudes from sea level to 40,000 feet. Developed under joint sponsorship of the Air Force, Army, and Navy, the Firebee has an unusual capacity for future growth. Its speed, high-altitude performance, and load-carrying qualities have encouraged constant refinement and indicate additional potential applications. Capable of being launched from a mother plane or from the ground, a two-stage parachute permits recovery of the drone with little or no damage. By no means its least important asset, the Firebee can be manufactured at less than 1/10 the cost of man-carrying aircraft of similar performance converted to remote-control drone airplane use. The Firebee is composed of 5 major assemblies: fuselage, wing, empennage, engine nacelle, and parachute cone. 4 of the 5 components are fitted to each other by means of conical fittings and self-aligning bolts. The drone missile can be assembled by 2 or 3 men in less than 1 hour. A Fairchild J-44 turbojet engine of approximately 1,000-pound static sea-level thrust powered the bird in most of its early flight. This engine is approximately 6 feet long, 22 inches in diameter, and weighs 300 pounds. The final assembly operation is the attachment of the engine nacelle to the fuselage. A lightweight A-frame is the only mechanical aid required. The forward pair of nacelle bolts act as hinge pins, allowing the after end of the nacelle to be lowered for easy access and servicing of the engine. This version of the Firebee has as its power plant the J-69 Marbury engine, developed in France and to be manufactured in this country by Continental. The speedy drone missile has a wingspan of approximately 12 feet and height of 6 feet. Less than half the size of present-day jet fighters, the Firebee is 18 feet long. Its empty weight is 1,200 pounds, and gross weight with 100 gallons of fuel is about 1,800 pounds. Constructed of aluminum, magnesium, some stainless steel, and plastic, the complete drone is shipped from the Ryan plant in a group of 4 containers with a total weight of but 2,500 pounds. Over 4 years ago, the initial test program was begun at Holloman Air Development Center, Alamogordo, New Mexico, under Air Force direction. Before any Firebee flight, a careful pre-flight check of the entire bird is conducted. The electronic equipment is given a careful bench test prior to installation in the drone missile. Easy access to all interior areas of the Firebee facilitates installation of flight control gear. Ryan engineers take full advantage of each flight to study the airborne performance of the drone. Here, carefully calibrated telemetering gear used to record in-flight data is installed in the wing. Electrical power and a flight control box enable the crew to simulate in-flight control surface motion. In the mobile radar station, the remote control panel is plugged in. From this point on, the operator will see the Firebee only on the plotting board. Radio contact has been established with the launching aircraft and the chase plane. An F-86 pilot provides a running commentary. The target engine has been started.
Transfer to internal power, prepare for release.
The final countdown begins.
Minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, you're up. Are you clear? What do you say, chase plane? Chase plane in, the top is very nice, it's holding straight and level. Wait a minute. Still descending just a little bit, leveling out and holding a straight course. The missile should stay at this altitude now for the remainder of the flight. Please notify us of any deviation. Roger, will do.
The remote control station tracks the bird and commands the flight from the control box.
Where's your airspeed? Now, please. Stand by. I'm latching on to him. I'll give you a good accurate airspeed in just a second. I got about 380 here, and my altimeter is 20,500. This was leveled out. I'm latching on to him right now. Roger.
The other range facilities are now busy at work. The optical and radar tracking equipment is constantly following the target in flight. Command signals to the drone go out over the radar system. The commentary between the remote control station and the chase pilot in the F-86 goes on steadily.
I'm gaining on the missile now. You walked off and left me there for a while. The missile rolled out and rolled right into the left bank again. I have an indicated airspeed of 340 and just about holding my own with the missile, maybe gaining a little. Altitude is 20,200. The missile is in a gentle climb. Altitude approaching 20,500.
Watch closely now for the parachute recovery, which is commanded at the end of the flight test.
How's the recovery, okay? Well, the recovery is pretty good. Your altitude now is just a little over 20,000, almost 21,000. It popped out okay. Roger, that's it, I got it.
While the parachute is descending, the chase plane radios a probable touchdown point to the ground control station. Recovery of the drone missile frequently takes the pickup crew into rugged, often trackless terrain. As the missile is lifted from the desert brush, it can be seen that damage is relatively superficial, confined almost entirely to the skin of the engine nacelle. Note the easy-to-handle recovery cart employed by the pickup crew. These insignia indicate successful flight and recovery of the drone missile. This particular Air Force Q-2 has completed 7 successful recoveries after flight missions. The Navy, most recent of the services to utilize the Firebee, is currently conducting its analysis and evaluation at the U.S. Naval Air Missile Test Center, Point Mugu, California. Special flotation tests of Navy Firebees were necessary since the KDA-1 targets must be able to float long enough to be located at sea and recovered. The bird has a surprising buoyancy, particularly after fuel depletion. Flotation is expected to be a standard requirement on future Firebee models. Following hangar checks, fueling, and final weight and balance checks, the target plane is wheeled to the flight line for loading aboard the launching aircraft. Navy test specifications call for a wing launch. Here the bird is hoisted into position and secured to the outboard wing bomb shackle. The launching aircraft is ready to take off with the Firebee firmly secured in the wing launch position. The mother plane can take off with a Firebee under each wing. During flight testing, a chase plane is utilized to observe and relay to the ground control center information about the behavior of the drone in flight. Immediately prior to the drop, the missile's controls are given a final check. Everything is satisfactory. The bird is ready for release. Stand by. Bird away. Control now shifts from the mother plane to the ground control station, which will put the drone missile through its paces over the test area. With the aid of a radar plotting board and a small black control box, the ground crew is in complete charge of the flight. Recovery of the Firebee is initiated in one of several ways: loss of command carrier, depletion of fuel, a critical hit by gunfire, or by command upon completion of scheduled exercises. On any recovery command, the 5-foot drag chute flares out first, bringing an initial sharp deceleration to the Firebee. After a given interval, the drag chute pulls the main parachute container to the rear, and a large 70-foot canopy is deployed. Rate of target descent is approximately 20 feet per second. When the drone touches the water, an automatic disconnect separates the chute from the Firebee instantly, and the main canopy slowly collapses. At sea, this prevents the drone from being dragged off balance and taking on water internally, with increased probability of loss by sinking. On land, the separation prevents strong wind gusts from dragging the drone on the ground, with inevitable subsequent damage. Hoisting the bird and its parachute aboard a recovery boat is a relatively simple operation in normal seas. A short bridle is attached to the risers, and the drone is quickly lifted aboard. As soon as possible, the bird is returned to the shop for thorough inspection for any damage sustained in the drop. The engine is partly dismantled. The shell is dipped in a tank of fresh water, while the internal parts are carefully lowered into another tank filled with Textil. After a thorough washing, the parts are cleaned and the engine reassembled and reinstalled in the nacelle. Meanwhile, all the non-watertight components of the drone missile are washed in a freshwater tank, lifted, dried, and thoroughly inspected for traces of corrosion. The Army prefers to launch its XM-21 drone from the ground. An A-1 type rail launcher is used. The Firebee has also been launched from the Ryan zero-length launcher, shown here mounted on its rotable cart. In both rail and zero-length launches, the target is boosted aloft by a rocket assist of some 11,000 pounds for a period of 2 seconds, following which the target jet engine provides the necessary flight stride. In its research, Ryan has drawn upon experience gained in developing the Ryan Firebird, the first U.S. Air Force air-to-air guided missile, as well as the Ryan Fireball, the first combination jet and piston engine airplane. In addition to its aerodynamics accomplishments, Ryan has pioneered extensively in the field of automatic navigation, electronic guidance systems, and control systems for flight vehicles of the Firebee type. The Firebee is no longer an experiment. As a production item, it offers the services an economical, efficient means of training air-to-air gunners and anti-aircraft personnel, and of evaluating missile and advanced fire control systems. Produced for less than 1/10 the cost of man-carrying aircraft of comparable performance converted into drones, the Firebee's recovery system permits repeated use of the target. The Ryan Firebee is the most efficient means of providing modern weapons evaluation and training to the men who man America's defense systems.